All right, so now that we've done all this math and we kind of showed some plots, we compared the time domain with the the frequency domain with the time domain. I really want to take the time to just conceptually take a look at what's happening in our circuit. So we've done a lot of math, we've done a lot of theory, but conceptually, what is actually going on? So again, let's just draw our circuit. We've got a sinusoidal input, we've got a resistor, we've got a capacitor, and we know that the resistor and capacitor basically form, they each have their own impedance, right? 1 over J, I'm going to write it in terms of F here, 2 pi F C, right, for the capacitor and R for the resistor. And then, of course, my input voltage is V in, my output voltage is V out. Well, I guess in this case I have it called V out and V in, but previously I was using VO and VS. We'll just call them V in and V out for now. And of course, I'm letting frequency in this circuit vary. And I'm looking at different frequencies here. And so what we notice is that R is completely fixed. It's not dependent upon anything. The impedance of the resistor is always R, no matter what frequency we are operating at, right? But the impedance of the capacitor strictly depends on the frequency, right? Of course. So if I vary the frequency, the capacitor's impedance changes, okay? So that's a very, very important concept. And so let me just redraw this. And maybe you haven't made this connection yet. I hope you have. Probably I may have even talked about it already. But if I draw these, I can just redraw them as two impedances. And this is going to be ZR, and this is going to be ZC. And of course, I still have the same V in and the same V out. But what I'm looking at is a voltage divider. I'm really just looking at a voltage divider, where instead of having two resistors, like I had in EE220, I have two impedances, the impedance of a resistor and the impedance of a capacitor. So what happens to this impedance if this frequency is really, really small? Let's say it's 0, like a DC circuit, right? Where the frequency is 0, nothing's changing. Well, if this value goes to 0, what happens to this impedance? This thing's going to blow up, right? The impedance is going to be huge. It's basically going to be infinite. And so what would happen in this voltage divider if I had an infinite impedance here, right? If this impedance, sorry, I'm grabbing the wrong tool. If this impedance were infinite, I would basically have an open here, right? If I have an open here, no current can flow in this circuit, and V in is going to be equal to V out, right? The current through this resistor or this impedance would be 0, right? And so then V out minus V in over R would have to be equal to 0. And the only way for that to be the case is for V out and V in to be equal to one another, right? So V out would have to be equal to V in, right? And that is exactly what we see at low values for the frequency, right? If we're at DC, which I don't even have plotted here, but down here somewhere off the plot at 0 hertz, I'm sitting at a ratio of 1, right? We saw that already. 1 meaning my output and my input are equal to one another. Because again, remember that this is the rate, even though I didn't plot it here because I'm a clown and I should have, this is V out over V in, assuming V in equals 1 volt. That's what I did here. I just let V in equal 1, and or an amplitude of 1 volt basically for my input signal. And so I only plotted V out. But just notice that that's what's happening here at a low frequency of 0 or even at 1, 2, and even out to like 10 hertz. I'm getting that this output and input are basically equal to each other. So even when I don't have DC, I still have such a tiny value for F that this impedance is so huge that the vast majority of the voltage is dropped across this resistor, and the current is roughly equal to 0. Or sorry, I'm saying I said that wrong. The vast majority of the voltage is dropped across this capacitor because the impedance is so massive. The current is absolutely tiny, and so the voltage drop across this resistor is effectively 0. So we get that the output is equal to the input. And that's what happens at low frequencies, right? So we've taken care of the low frequencies. What happens at high frequencies? Well, when f is really, really, really high. So when f is a really large value, so let's say we let f tend towards infinity, then I get a short here. It's no longer an open, it's a short. The impedance of the capacitor, right, if I have f towards infinity, this whole impedance goes to 0. And the impedance being 0 is equivalent to just having a short circuit on the output. Well, now what is V out? V out is 0, right? It's shorted to ground right through that short. And that's exactly what we see on the plot at high frequencies. We see that, you know, at low frequencies, we just said that it was an open, so we get these, the voltage at the input and the output to be roughly the same. Here we get the voltage at the output to be 0, right? The V out over V in is going towards 0 because I am basically tending towards the point where this is a short circuit and I get no voltage at the output. And so all the frequencies in between 0 and infinity, right? Well, in this case, that I basically use the very extremes, but in my circuit, I really could have cut it off from about 10 hertz to about 100 kilohertz, right? So for frequencies between 10 hertz and 100 kilohertz, that is where I get interesting behavior, right? I have something happening that's not just a flat ratio of 1 or a flat ratio of 0. I have all this interesting stuff happening. And somewhere in the middle, I get a value of 0.5, which means the same amount of voltage is dropped across both elements. That is the point where the impedance of the capacitor is equal to the impedance of the resistor, right? Which is a crazy concept, but it is the case. That is where these two impedances in my voltage divider here are equal, so I get V in to be 1, V out to be a half, and I have 0 here, and that occurs right here at not too far below 300 hertz, right? And so that's what's happening intuitively when we look at this circuit. We're basically just saying, okay, so I have different frequencies. The impedance of one of my components is changing. And since the impedance of one of my components is changing, as I change the frequency, then the output and the current and all kinds of other things in my circuit are changing as well. And in this particular circuit, we chose to look at the transfer function V out over V in. So what we've been monitoring is what's happening to my output voltage as I vary the frequency. Again, I said when we talked about transfer functions, it could be any number of things that we're interested in. It could be the current through this device, it could be the current through this device, it could be, and circuits get much more complicated, it could be any current and any voltage in the system that we're interested in basically monitoring as we vary the frequency. But here we chose for it to be the ratio of V out to V in, so that's what we've been monitoring this whole time. And so I'm going to go ahead and end this video here. Hopefully this makes sense. If you have any questions, please feel free to ask. And in the next video and the next couple videos, I'm basically going to solve another example. Now that we've gone through all this context and all this explanation, I'm going to solve another example where we do the whole plotting and all that all over again, but for an RL circuit. Okay, so I'm going to go ahead and end this video here.